Hey everyone, I'm just waiting for everybody to enter the Zoom room. Zoom room.
I had a quick question.
Go for it.
Are we starting with chapter 17 today?
No, 17 will come later. We're starting actually with chapter, I think it's 21. Let me double check. I always forget the numbers because I'm doing so many different courses. No, it looks like it's chapter 20. No, it's not that either.
Oh, you had to eat up Bible to you.
Here's the I'm using the wrong textbook. I was looking at my textbook from 202, not 241. Oh, I'm getting ready to make a mess now. Let me double check. I do think it's 21. Yes, definitely 21. We will go back later and hit 17. I think that, if I remember correctly, that's my plan, or that's the course plan.
Yeah, but the homework problems are on 17 and 18.
Are they posted already? I didn't think I posted those yet.
On Pearson.
Okay.
Yeah, they're posted and they're due on the 31st.
Okay, skip those. I mean, if you started them, that's great, but don't worry about it. I'll clear your trial out unless you were happy with the grade, in which case I'll leave it. But yeah, I don't know how I did that. I thought I put up 21 and 22, but I'll fix that as well.
Okay.
What's that?
They're there also, but they're due on the 7th of September. So
I said it's a little bit better.
Okay, so that sounds a little better.
If I want to cross one of the big signals, I'm grabbing it.
So 21 is there? Is that what you're saying?
yeah, 21 and 22 are there, but they're due.
Okay, good deal. I just want to make sure they're there. Do focus on 21. That's what we're finishing hopefully today. At least a good fraction of it. Between that and the videos that I've already posted from YouTube, from my YouTube channel, but I also posted on Canvas. From that, I think y'all can get everything done for chapter 21. That reordering of my books I did a second ago. Oh yeah, everything just fell. So I did not have an earthquake. There was no earthquake. It sure looked like it. You'd be surprised. A box of napkins or Kleenex is not quite sturdy enough to hold up 6 books. So looks like everybody else has got. So Bucky, you have a question, sir?
Yes. Can you hear me?
Yes.
I had a lot of trouble finding where to buy the lab book.
You actually buy it from the bookstore. The good news is it doesn't matter for today because I have the first lab printed out because we normally expect everybody to, not everybody to have it on the first day.
Okay.
So you're okay for today as far as lab goes. But yeah, you buy it from the student store at the Virginia Beach campus.
Okay, I can get that shipped, correct? Somewhere?
Yeah, it might take a little while, but yeah, you should be able to get it shipped.
Okay, because I live in Roanoke.
Okay, yeah, you'll probably need that shipped then.
Yeah. Yeah. Okay, thank you.
If once you show me that you've purchased it, I can actually, if you run short on a lab, I can justify giving you another lab if it doesn't come in time. So don't worry about that. Just but keep your receipt and your shipping order or whatever, so you can show me that, and then I can individually give you a copy of whatever labs you don't have, but till the thing comes in.
Okay, thank you very much.
No problem. Anybody else have any questions?
My name is D-Manny. I had some questions, but probably I'll ask you after class. I just switched over from, what's his name?
Ippolito?
Huh?
Mr. Ippolito? Or you talk about for this class, you switched from 202 to 242 maybe?
Well, it's 242 with another professor. I forgot what his name was.
Oh, maybe Hep or Hale.
Hep,
yeah, got you.
Just
no problem. You haven't really missed much because all I did on the first day was cover the syllabus. And I did show a couple of videos to explain charge conservation, induction, stuff like that. I think from reading the first chapter, which is chapter 21, you can get those concepts. Today is where I start off the more mathematical stuff, so you haven't really missed too much.
All right.
And especially if you've already had his class for one day. Okay. Anybody else? I'm assuming that was the same raised hand, Bucky. You didn't have another question, did you?
I'm
Okay.
sorry. Yes, that was correct.
Okay, no problem. All right, so last time I talked to you a little bit about charge induction, conductors, what they are versus insulators, and I gave you some videos. I also posted initially posted a bunch of links to some Tesla coil videos, which I find are really cool. One of these days I'm gonna make one. Well, if I don't die in the process of trying to make one. But I really want to make one, so I put those up just for your entertainment value. And then I realized, well, that takes up a lot of my modules, so I just put them all in a single PDF document, put the links in there. Oh yeah, Kadeem, one thing I did let everybody know last time was that I post these videos on YouTube, so if you don't want your name seen, I would probably just put your first name up there. And then also, if this one's a problem because your name is already up there for at least for a few seconds, just let me know and I'll blur it out before I put it up. Usually people don't care, but I just always do that just to make sure I'm not, outing a secret witness under protection by the FBI from the mob or something, Well, at least that's where my brain goes. All right. So I guess we'll go ahead and get started. What we're going to do today is we're going to talk about Coulomb's law, and then we're going to explain how Coulomb's law kind of bothered everybody, but we fixed it by making up some stuff. And then we found out that the stuff we made up was actually real. And so I'm going to talk about all that. It's a kind of a neat thing, and it's how science works out in many cases. It's exactly the same of what happened with gravity, for instance. So it was actually postulated by many people. Coulomb was one, Cavendish was one other, Ben Franklin was another one. And they all seem to have come across the same decision at the same time. And that was, it turns out that two charges are repelled if they're alike charges and are attracted to one another if they're unlike charges. We do know, for instance, Ben Franklin was the one that ultimately gave the charge the signs that they have, which is kind of a bummer because he sort of chose it in such a way that we actually turn out to think the opposite of what reality is, in that when we talk about currents flowing, from the positive terminal of a battery back into the negative terminal, that's the behavior of positive particles moving around. Because he chose that particular type was a positive, we've got that picture in our head, but in reality, it's the negative charges leaving the negative terminal of the battery going the opposite way. The good news is there's only one experiment you can really do to tell the difference between positive particles going one way and negative particles going the other way. So he didn't hamper us too much. So it's not that big a deal. But still, it's kind of cool to think that old Ben Franklin, here in America, in the backwoods of America, around the same time as these other great minds, and was coming up with the same stuff. And actually, he was not formally educated. He sort of taught himself everything. So his only weakness was math, and still he came up with Coulomb's law. So Coulomb's law says that the force, whether it be attractive or repulsive, depends on whether the charges are alike or not like, in which case they attract when they're unlike charges and they repel when they're like charges. And the force is proportional to the product of the charges. So that means if you double one charge, you double the force. If you double the other charge, you now double the force for that one. If you triple one and double the other, then you sextuple, because 2 times 3 is 6, you sextuple the force. That's part of it, okay? The other thing that's about Coulomb's law is that it's inversely proportional to the square of the distance between them. So you guys have already had 241 and y'all talked about gravity. So you'll see the equation is identical to the equation of gravity, except we replace charge with mass, we replace mass with charge. But what the 1 over r squared means is if you double the distance away between two charges, if they had a force, say, of 100 newtons before, and then you double the distance away, now they're going to have a force not of 50 newtons, but of 25 newtons, because the distance goes like r squared. So the force is 1 over the distance squared. So that's a kind of neat thing as well. And then the final part was the direction, because remember, force is a vector quantity, so it has to have a magnitude and a direction. So I've given you sort of what you need for the magnitude. All you need to do is do an experiment now, because F is proportional to Q1 times Q2 over r squared. All you need to do is one experiment and determine out what that constant of multiplication is, and then you'll have the actual Coulomb's law. Okay, and so I'll give you that in a second. We have a question. Yeah, there's no course ID for this. The course ID is what you use if you go to Pearson by yourself. I've got my course integrated, so you just go straight into Canvas. And when you get into Canvas, you click on My Lab and Mastering, and they ask you to register. And if you've already done that, of course, your registration will already be there. So there's no course ID. You just jump right in through Canvas by clicking on My Lab and Mastering. All right, so back to Coulomb's law. So one experiment would get us what that constant of proportionality is. And in fact, the experiment was done. Cavendish was one of the people that did it. And basically what they did was take two masses on strings, or in this case, two charges on strings. So basically they had two charges here and here connected together by, a rod that was probably an insulator, and they mounted that on a device. And then they took two more and put it right next to them, so the two masses were next to each other. You'll see a diagram in a second. Actually, the diagram is on the it's actually on the picture for the lab course for this course. But anyways, that device caused the charges to attract each other and twisted one of the two sets of charges a certain amount, and then using basic engineering laws about torsion, they were able to determine the constant. So that was actually how they did it. So let me start off by giving you some concrete examples of this and actually giving you the equation. So I'm going to switch to my document cam. Anybody have any questions before I start that? All right, so here's a document cam. So this is Coulomb's law. It says the force in magnitude, notice I have no vector symbols on here. The force in magnitude is equal to some constant K times Q1, Q2 over R squared. Turns out that constant K is about 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. And that is to 2 sig figs 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. I like to point this out. Does anybody know what 1 over 9 is as a fraction, or as a decimal, I should say?
Is 1.1111.
Exactly, 0.1111. So keep that in mind. That sometimes makes my examples a little easier. We will find later that this is not the best way to express the force with this constant K. In fact, the constant we normally use is 1 over 4 pi epsilon naught.
Sir, excuse me.
Yes. Can y'all see this, or is it out of focus or anything?
Yes, it's out of focus.
Okay, let's try that.
It is out of focus.
All right, thank you for that. I'll zoom it closer as best I can and put it really crooked. That helps things. Now I'm gonna wipe some mayonnaise on the lens. That should do it good. Okay. Is that now in focus? It looks focused to me, so I'm thinking the focus might be a problem more of bandwidth. Does it look okay now, everybody?
It's better, but it's still not perfect.
Okay. That's the
Yeah,
worst
I think
part.
it's bandwidth because looks pixely.
Yeah, pixelation. I'll bring it a little closer and that'll help a little bit too. And you can also refer to your book, but just going over what we had, it's K, Q1, Q2 over R squared, where K is 8.99 times 10 to the 9th to 3 sig figs, but to 2 sig figs is just 9.0 times 10 to the 9th. Notice the units are Newton meter squared per Coulomb squared. The Coulomb is the unit of charge. That's a ginormous amount of charge, by the way. It, for instance, is a typical lightning strike may only have 100 or a couple hundred coulombs of charge passing. And you know what that does to us. So lightning strike is pretty severe, and it only has a couple hundred coulombs, so you can tell that coulombs must be a pretty big unit. The other version is, instead of using a K, we use 1 over 4 pi epsilon naught. So K is actually 1 over 4 pi epsilon naught. I'm trying to write a little bigger since we're having pixelation problems and all that good stuff. So when we use this form, then we actually have to type in 4 and pi and epsilon naught, but epsilon naught is 8.85 times 10 to the negative 12th. Notice it's in the denominator, so the units will be exactly the opposite. Coulomb squared per Newton meter squared. I usually do that as a nice little example of how to work out your units. You know, on this side, for instance, that's got to be a Newton. So I've got to have a Newton in the K, and it needs to be in the numerator because that's going to be the answer. But I need to cancel out 2 coulombs, so that tells me to put Coulomb squared in the bottom. And I also need to cancel out 2 meters, so I have to put meter squared in the top. So that's just good practice things you should do. So as an example, to just get your feet wet, let's consider, for instance, an electron in the Bohr orbital around the nucleus of a hydrogen atom, i.e. a proton. So it turns out the electron charge and the proton charge have the same magnitude. It's this number, it's this symbol E, 1.602 times 10 to the negative 19th coulombs. So that's the actual charge. It turns out the Bohr radius, i.e. the distance from the center of the proton in some sense to the center of the electron, which actually makes no sense because the electron has no physical size. But let's go ahead and calculate the force of, and let's ask this, is it a force of attraction or a force of repulsion between a proton and an electron?
Attraction.
Yeah, it is attraction because they're opposite charges. Very good. Now here's the deal. Whenever we use this, we don't put the signs in, okay? Don't mess with the signs. When we start to do integrals with the version of this for the electric field, then we'll deal with signs. But right now, we don't want signs at all. We're just going to find the magnitude, and then we'll create a vector to associate it with its direction, okay? So right now, I'm just asking for a magnitude. So it turns out the force between an electron and a proton would be 9.0 times 10 to the 9th Newton meter squared per Coulomb squared times 1.602 times 10 to the negative 19th coulombs. That will be squared because it's Q1 times Q2. And remember, I'm ignoring the signs. I just want the magnitude. So I just multiply it by the same number twice. And then I divide it by the square of the distance, which is that Bohr radius A0. So that's 0.5292 times 10 to the negative 10th meters. And that's going to be squared. Okay. When I actually compute that, what I get is, and I'm doing this on the fly, so bear with me. So I'll do 9 10 to the 9th times 1.602 e to the negative 19th. I'll square that. And now I'm going to divide it by 0.5292 e to the negative 10. And I'm going to square that. And I get 8.2, actually 8.25. That's an extra sig fig, by the way. 8.25 times 10 to the negative 8th newtons. So that's a force. I mean, we have an actual unit of force here, so that is a force. But is it really big? I don't know. Well, let's compare it to the gravitational attraction. So the gravitational attraction for this would be the same equation, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Now we have to use the mass of the proton, which is 9.109 times 10 to the negative 31st kilograms, times the mass, or that's the electron mass, excuse me, times the proton mass, which I will double check my memory, but I think it's 6.73, looking, 1.67, glad I checked, 1.67 times 10 to the negative 27th. 1.67 times 10 to the negative 27th kilograms. I remembered the magnitude, but I forgot the mantissa part. So that's the numerator, and it's still going to be divided by 0.5292 times 10 to the negative 10th meters, all squared. So if I compute all this, and I know there's an easier way, I could just cancel out my factors and figure out what F over FG is or FG over F is, but I'm just doing it brute force just so you'll see. So I do 6.67 e to the negative 11th times 9.109 e to the negative 31st times 1.67 e to the negative 27. All that's going to be divided by 0.5292 e to the negative 10 squared. Ooh. Bad things happen. E to the negative 10. And now I'm going to square that, baby. This time I get 3.62 times 10 to the negative 47 newtons. So you can see that the Coulomb force is actually on the order of 10 to the 41 times stronger, or excuse me, 10 to the 39 times stronger than the gravitational force. So yeah, it's a big force. And that's why we pretty much ignore gravity whenever we're solving physics problems involving electricity and magnetism. So does everybody see how we did that? It's just a simple formula, just like you did with gravity, only now we're using a different constant and we're using masses instead of charges. All right, so let's look at another problem, and now we're going to actually start getting into the problem of dealing with vectors. Okay, in other words, I got to take into account the fact that these are vectors that have not only a magnitude but a direction. What I have is three charges sitting along a line. The line has a total length of 4 meters. This charge, Q1, has a charge of -4 millicoulombs. I realize that's really small. Make sure everybody can see it. Okay. The charge on the left, Q1, has a charge of -4.00 millicoulombs. The charge in the middle, Q2, has a charge of 4.00 millicoulombs. And then the charge on the right end is Q3, and that has a charge of -0.11 microcoulombs, which I went ahead and wrote as 10 to the -6. Okay, everybody see that problem now? So what I'd like to know is, what is the total force on the charge Q3? That's not that focused now that I moved it, so I'm gonna, here you go. So what is the total force on 3? Well, the force on 3 is equal to the force on 3 due to 1 plus the force on 3 due to 2. In other words, the superposition principle works. Basically, forces add. So if you find the force that Q1 is applying to 3, and then you find the force that Q2 is applying to 3, you just add them, and that'll give you the total force on Q3. So what I'm going to do is I'm going to calculate the magnitudes of F31 and F32 using Coulomb's law, and then work out the signs so I know what's going on. The good news is this is the simplest of all vector cases because they're all along one line. So when I say direction of a vector, I mean positive or negative. Does that make sense? So F31, notice I've dropped the vector symbol. F31 is, the magnitude is 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. I do suggest you write these units every time, at least during tests and homework, so you can catch yourself in little errors from making little errors. Now I'm going to say that's times 4.00 times 10 to the -3rd coulombs. And again, we're ignoring the sign. So the other one is also negative, but it's 0.111 times 10 to the -6 coulombs. And of course, the distance between them is 4 meters. So I think you can tell what's going to happen here. This 9 is going to cancel out with that 9, 1/9 basically. And then 10 to the -3rd times 10 to the -6 is going to give me 10 to the -9. So that's going to cancel out with that 10 to the 9. So really all I'm left with is 4 over 4 squared. So it's 0.25 newtons. And notice F3 and F1, or Q3 and Q1 are both negative, so they're repulsive. So that means Q3 is trying to get away from Q1. So I'm going to say to right, which is what I'd call the positive direction. Okay. Now F32, now you see why I chose my numbers like I did, is 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. And that's going to be Q2, which is 4 microcoulombs times 10 to the negative 3, excuse me, millicoulombs. Again, dropping the signs, they don't matter. 0.111 times 10 to the negative 6 coulombs. And all that will be divided by 1 meter squared. Okay? So these two charges, notice, had the same magnitude. So you sort of might think, well, maybe they'd be about the same force, but notice what happens, how much a bigger effect the R squared has. So in this case, again, this 0.111 is going to cancel out with the 9, the 10 to the negative 3, and 10 to the negative 6 is going to cancel out with 10 to the 9. So all I'm left is with 4 on top over 1 meter squared. So this one turns out to be 4.00 newtons. Okay, and technically speaking, I really should eliminate these last two, or excuse me, no, that one's fine. I should eliminate that digit because it's not really correct. Now this one, the Q3 and Q2 are actually attractive because Q3 is negative and Q2 is positive. So Q3 wants to be pulled this way. So I'm going to say to left. Okay, I know that's a horrible looking left, but luckily I said it out loud. So the total force.
Professor,
Yes, ma'am.
could you explain why it goes to the right and the left again, please?
Okay, so what you got to do is consider E, and this is the big thing, so it's good that you asked that. A lot of students have problems with this. So when I was doing 3-1, that was the force on 3 due to 1. Well, 1 is a negative charge, and Q3 is also a negative charge, so they repel one another. So you imagine, let's say, all of the charges except for Q3 fixed where they are. They can't move at all. Ignore Q2 for a second and think, since these two repel, which way does Q3 want to go? That's the way I do it. So the fact that this one and this one are negative says they repel each other. This one's stuck where it is, but if this one were free to move, it would take off that way. Sort of like pushing two north ends of a magnet together. If this was a north end of a magnet and this was a north end of a magnet, as I slowly push the magnet this way, this thing would take off that way, again to the right. Does that make sense?
Yes.
Okay, the other thing is, remember the other law about Coulomb's law. You remember I told you the formula gives us the magnitude, but the direction is always along a line connecting the center of masses of the two charge, or the center of charge of the two charge, basically. So these are point charges, so the force has to be along this line. So it's either attractive, pulling it towards Q1, or it's repulsive, pushing it away from Q1. Since this one was repulsive,
okay, I think.
You got it now?
Yeah.
Okay, cool. All right, so you only can have it act along this line, and since it's repulsive, it's going to have to go to the right. Similarly, you can only have it go across this line because both of these are on the same line as well. But in this case, it's a positive charge and a negative, so Q3 is attracted to Q2, so it's going to go to the left. So ultimately, my force F, and I'm going to put the vector symbol back on it, F3 is going to be 0.25, which I call the positive direction, minus 4.0, so it'd be negative 3.75 newtons. Again, this digit's way fake, okay? So I'm using, oh, I wrote it out of your view. So I am using this negative sign to indicate a vector. What I would technically do is if I called this guy up here the x-axis, then I'd say negative I hat. And that would take care of it. Or I could just say F3 is equal to 3.75 newtons. Again, double underline that, to the left. And that would explain it as well. Okay. Of course, there's other ways too. You could say in the 180 degree direction. So you say at 180, then everybody understands, oh, you're meaning from counterclockwise from the positive x-axis. So whoop, points that way. Does that make sense to everyone?
Are you hard on us about when it comes to significant figures?
No. In fact, I've been making, because I have so many students, I've been making my tests multiple choice, but the homework system is kind of hard on you. I try to make it loosen up as much as I can, but the homework system is basically geared towards using proper sig figs every time. So you got to be a little careful on that, but not on a test. That makes sense to everyone?
Yep.
All right, so now we're going to have to graduate from kindergarten and go to first grade. And I'm being facetious. That's what my my PhD advisor used to say. He says, this is just some calculus like you learned in kindergarten. So I always thought that was kind of funny, and it gave me a little sense of peace. Other people, it gives a sense of, ah! But no, I mean it as a sense of peace, so please take it that way. So let's look at another problem. This time it's going to be more one of a vector nature. So we're going to have to really deal with a vector. So let's say, for instance, we have an XY coordinate system. And this is my y-axis up here.
Excuse me?
Yes.
The writing on this page is very dim, so it's very difficult to see.
Especially with seeing through it? Okay, let me see if I can do that then. Let me also see if I can bring it just a little closer. And try to get it in focus. Okay, so let's start over. I'm going to draw a y-axis. And I'm going to draw an x-axis, and I'm only going to need pretty much the top half of the y-axis. So that's why I drew it that way. Okay. This is normal. I normally draw x to the right, y up, and then, of course, z has to come out of the page if I have to go 3 dimensions. But what I'm going to do now is I'm going to take a charge and put it right here and say this is a distance of 1 meter. And since it's on the negative x-axis, it's -1. And then over here, the distance of 1 meter. And I'm going to say that's an infinite number of decimal places. In other words, it's 1.000000. Okay? This one's going to be a charge of -0.111 times 10 to the -6 coulombs. In other words, 0.111 microcoulombs. This one is going to be a charge of positive 0.111 microcoulombs. So I figured I'd put the actual prefix in there so y'all get used to seeing that as well. And now I'm going to go up from here. Let's go a distance of, say, 2 meters. Again, infinite number of decimal places for that. But instead of putting the charge there, I'm going to go straight above this and put the charge right here. And this one's going to be 4.00 times 10 to the -3rd coulombs again. Okay. This one's going to be called Q1. This one's going to be called Q2. And this one's going to be called Q3. And I want to know the force on Q3. And notice that is a vector quantity. A force is a vector quantity. So when I say I want to know the force F3, then that means I need the magnitude and direction. So this is where things get a little hairy. Okay. What you see is here is pretty straightforward for the force between these two. But over here, I got to do some little trigonometry to figure out how far apart they are. So what I do is I'll say F3, like I did before, is equal to the force due to, or on 3 due to 1, plus the force on 3 due to 2. Okay. I can calculate the magnitudes like I did before, and the magnitude for the 3-2 one will be easy. So let's do that one first. F32 is going to be 9.0 times 10 to the 9th. I'm going to leave off the units this time because I'm trying to fit on the paper. The charge is going to be, again, dropping the signs. All I care about is the magnitude, 0.111 times 10 to the negative third. And then 4.00, or excuse me, that was supposed to be 10 to the negative 6. Everybody catch that? I changed it to negative 6. And 4.00 times 10 to the negative third. Now the distance between them is clearly 2 meters. And that has to be squared. So again, the 0.111 cancels out the 9, the 10 to the negative 6, and the 10 to the negative 3 cancels out the 10 to the 9th. So I'm just left with 4 over 4 meters squared. So that ends up becoming 1.00 newtons. Now I can actually make that a vector quite easily because I know that this is a negative charge and this is a positive charge. So they attract or repel. Attract, very good. And I know the force acts along this direction, which is parallel to the y-axis, right? So according to this force, it wants to be pulled straight down towards this guy as a result of this guy alone. We're completely ignoring that one. So I can actually call this negative j hat to represent a vector. So I'm going to say F32 as a vector is -1 Newton in the j hat direction. Okay, the negative just indicates it points down as opposed to up. Remember, when you multiply a vector by a scalar, if the scalar is positive, the direction stays the same. If the scalar is negative, the direction flips by 180, and everything else, the number just actually somebody's trying to get in. Everything else, it just shrinks it. So if the number is smaller than 1, you make the vector smaller. If the number is bigger than 1, you make the vector longer. So we now have the force F32, and we even got it in vector form, so that's really nice. Now I'm going to do F31. Actually, I'll leave off the vector symbol right now because I'm trying to do the magnitude. And what you see is this distance from here to here is 2 meters, and this distance from here to here is 2 meters. So if this is 2 and this is 2, this is 2 squared plus 2 squared. That's 4 plus 4. And then we got to take the square root of that. That's square root of 8. That's 2 root 2. Which is basically 2.822. Okay. That also tells us, since this is 2 meters and this is 2 meters, that tells us this angle is 45 degrees. If it wasn't 45 degrees, we just take the inverse tangent of this divided by that, and we would find the angle. But in this case, I know it automatically because the 2 legs of the triangle are equal. Is everybody cool with that? Does that make sense to you guys?
Yes.
This is where the vector stuff gets in, and if you didn't understand that, then that would be a problem. So now I'm just going to calculate the magnitude. It's 9.0 times 10 to the 9th times 0.111 times 10 to the negative 6 times 4.00 times 10 to the negative 3 over, in this case, 2.822 squared. So this has become a whole poop mess here, but you can see square root of 8 basically squared is going to become 8. So I have 4 over 8, and it didn't turn out to be a poop mess. I figured it out on the fly. So 4 over 8 is 0.500 newtons. Okay. Notice I couldn't just haphazardly throw an I hat or a J hat on there. What I have to realize is the vector does lie along this line. It always lies along the line from the center of one charge to the center of the other. Now I just got to figure out which direction it points. So this is the force on Q3. So is it attracted to Q1 or is it repulsed by Q1?
Repulsed.
It is repulsed. They're like charges. So it's like Brangelina. Yeah, I said that. Okay. So what we're saying is the force is actually on this one pushing this way. Everybody see that? So if you really wanted to take the time to draw another triangle, you would say 0.500 newtons, 45 degrees. This is F31 sub y, and this is F31 sub x, like that. I know I wrote that really small, but it's the same as that triangle up there, so I figured y'all would get it. What I do, and I strongly recommend you take time to do this because you're going to get stressed out in the test and you'll easily make mistakes. What I do is go ahead and do the sine and cosine no matter what. I go ahead and write sine of 45 degrees equals opposite over hypotenuse. So I see that's F31 y over 0.5. And then I write cosine of 45. Notice I'm not trying to just jump into which one's x and which one's y. I'm actually taking the time to write both of the trig functions and then working that out. This one becomes F31x over 0.5. So what I can see now is that, trying to make sure you all can see all this. Looks like you can see it there. So F31 sub x will be 0.500 newtons. Notice it points to the right too, so it's going to be a positive, times the cosine of 45 degrees, which you probably know off the top of your head, but the main thing is we want the actual number, so I want half of 1 over the square root of 2. So 0.5 times I got a fancy calculator, so it makes me mad. I gotta do 13 buttons to get to the cosine. And I get 0.354. I'm carrying an extra digit there, newtons. And then similarly, F31 sub y would be 0.500 newtons times the sine of 45 degrees. And of course, cosine and sine are identical for 45, so I get 0.354 again. So F31 as a vector is actually equal to, notice the 31y points up too, so it's also positive. So the F31 vector can be written 0.354 newtons I hat plus 0.354, oh, made a bad mistake there, newtons in the j hat direction. So both of them are 0.354 despite my drug addict looking handwriting. So I apologize for that. Now I just have to add these two vectors. I think that's pretty easy, as you can tell, because the only parts that are alike is the y component. So I'm going to take 1 from that. And of course, that's the bigger number. That's the bigger magnitude. So it's going to become negative. So I'll say 0.354 minus 1 should be about negative 0.646. So ultimately, F3 as a vector will be 0.354 newtons in the I hat direction. And you can also, if you forget which one's I and J and K, you can write this as X hat. That's fine with me. I use that all the time. And then this one, of course, is going to be negative 0.646 newtons J hat. That's one way you could express it. It's not the most transparent way to express it. I usually like magnitude and direction. So you got to watch out when I ask a question. Am I asking you for the vector, or am I asking you for the magnitude and direction of the vector? So always be able to do them. So let me show you how to do this. This is called decomposing a vector, or excuse me, in this case it's called building a vector, because it's already decomposed into components. So I'm sort of composing a vector, if you will. So what I'm going to do is draw the x and y axes again. There's my x-axis. There's my y-axis. What I have is a vector that's 0.354 newtons pointing to the right. So that is what I call a positive component direction. Okay, and then I have, in addition to that, a vector pointing negatively by about almost twice as big in the y direction. So in this case, I'm going to make the component red. And this should be 0.646 newtons. Okay, so there's my vector there. So the sum of these two vectors can be gotten, since they're tail to tail, by the parallelogram rule. And that gives me this vector right here. So what I want to know is probably the smallest angle. So I'll take this one. I'll call it phi. And I want to know that magnitude. So using the Pythagorean theorem, I can get the magnitude pretty easily. I'm going to say 0.646 squared. This is where keeping that extra digit was really helpful. Okay, because remember, it's technically this digit's not supposed to be there and this digit's not supposed to be there. Okay, plus 0.354 squared. That's 0.543. Now I take the square root of all that junk, and I get 0.737. So the magnitude from the Pythagorean theorem of F3, which we write like that, or we just write it without a vector symbol at all, is 0.737 newtons. Again, an extra digit there. Now the angle phi is equal to the tangent inverse. I usually use tangent. You can use anything, but if you're using sine or cosine, then you're going to have to use this number you already calculated. And there's some chance that has an error. So if you use one of the original two, you're less likely to use something that was erroneous. So maybe you'll get this part right and the other part just a little bit off. So that's why I do that. Tangent's opposite over adjacent. So it's, notice I dropped the sign, 0.646 over adjacent, which is, or excuse me, opposite over adjacent, 0.646 over 0.354. And I get 0.646 divided by 0.354. Take the inverse tangent of that. And I get 61.3 degrees. 61.2778, but I'm going to call it 61.3 degrees. Again, an extra digit on that. So I can say F3 is 0.737 newtons at negative 61.3 degrees. That's the most succinctly I can write it. I could also say at an angle of 61.3 degrees below the horizontal axis. I could say at an angle of positive 298.7 degrees, so on and so forth. There's a bunch of different ways. If this was north and east, then I'd say it's 61.3 degrees south of east. So that's another way you could do it. Any questions on that?
Yes, I have a question.
Yes.
Yeah, how did you get 0.646?
Okay. What that came from was, remember I had that 3,2 had a magnitude of -1 in the J direction.
Mm-hmm.
So I had to add 3,2 plus 3,1. So I added this vector and this vector, and that gave me 0.354 minus 1, which is negative 0.646.
Okay.
Let me write from F3 is equal to F31 plus F32. Do you see it now?
Yes.
No problem. Anybody else have a question?
Can you scroll down a little?
Yes.
Answer 'em.
Quick one. This 10 should be 10 inverse, right?
Yeah, thank you. Nice catch. I said it right, but I didn't write it right. Good job. Y'all are asking good questions. Y'all seem to be paying attention, following along. That's a good thing. That's the only way you're going to survive in a calculus-based physics class over the internet, guys. Sorry, I use guys as not a gender-based thing. That's just the word I use. If it offends you, I will try my best to not do it. So just email me and let me know. Do you think it would help you to see a recap of what we did step by step?
Yeah. Yeah.
Okay, let's do that. So now that I've made that top part or that bottom part available, so what we had was a charge Q1, which was positive 0.111 microcoulombs, a charge Q2, which was negative 0.111 microcoulombs, and then a third charge Q3 that was 4 millicoulombs, okay? And I asked, what is the force on Q3 as a result of Q1 and Q2? That would be called F3, the force on 3. The force on 3 is the force on 3 as a result of 1 plus the force on 3 as a result of 2. So I knew vectorially I just had to add those two. So that left me trying to find these individual vectors. Well, the fact that this was a dimension I knew, that said that I could make that magnitude calculation really, really quickly. So I did that one first. F32 is just Coulomb's law, where K is 9 times 10 to the 9th, Q1 is 0.111 microcoulombs, and Q2 would be, I know I said 2, I'm trying to go with the formula for Coulomb, is 4 millicoulombs. And the distance from my diagram is clearly just 2 meters. So I could write 9 times 10 to the 9th, 0.111 microcoulomb, which is what I'm using to get rid of the 9, and 4 times 10 to the negative 3rd coulombs over 2 meters squared. So this 0.111 cancels out the 9, 10 to the negative 6, 10 to the negative 3 cancels out the 10 to the 9. That leaves just 4 over 4 squared, or 2 squared, which is 4. So 4 over 4 is just 1. I realized that because this is negative and this is positive, it's an attractive force. So that means Q3 is feeling a force pointing downward, which would really have been helpful if my arm wasn't in the way. So the force F32 is in fact pointing downward. It's literally parallel to the y-axis, so I could just automatically write negative 1.00 newtons in the j-hat direction. Next, I had to calculate F31. Well, that required me to figure out what this distance was. Well, that was pretty easy because I set up the geometry nicely. Actually, I set it up better than I thought I did. So it's 2 meters this way because it's 1 meter from here to here and 1 meter from here to here. And then it's 2 meters that way. So it's 2 meters squared, which is 4, plus 2 meters squared, which is 4. 4 plus 4 is 8. So this is the square root of 8, which is luckily pretty easy to calculate because when you're going to square it, you're going to get back 8. So that worked out really nice. I multiplied 9 times 0.111 times 10 to the negative 6 times 4 times 10 to the negative 3rd and divided by the square root of 8 squared. So the square root of 8 squared is just 8. This up here was just 4. So 4 divided by 8 is 0.5. Everybody follow that part?
Yes.
It's just I happened to choose really nice numbers on purpose, but I didn't expect it to come out that perfectly. I expected to have some crappy number for this magnitude right here, actually. So now what I have is a magnitude of a vector, but I need a vector. I need a x coordinate, or excuse me, an x component and a y component. So I'm really just looking at this diagram, but I redrew it over here. So I now have a vector whose magnitude is 0.5, whose angle right here is 45, and whose x component is this part and y component is that part. I advised you guys to go ahead and use both trig functions when you're doing this so you don't make the mistake of just blindly choosing sine for y and cosine for x, because if you're using a different angle, it's not always that way. So I write down what is the sine of 45, and I use the old mnemonic, some old horse came a hopping through my alley. Some old horse came a hopping through my alley. So some old horse means sine is opposite over hypotenuse. The opposite is f31y. The hypotenuse is 0.5. Came a hopping is cosine equals adjacent over hypotenuse. So the adjacent is the one touching the angle. So that's f31x. The hypotenuse is 0.5. So all I had to do was take 0.5, multiply it by cosine. That will give me the x component, which is clearly pointing to the right, so it's positive. 0.5 times the sine of 45 turns out to be the exact same number because sine and cosine are equal at 45 degrees. And that happens to be pointing in the positive y direction, so that's also positive. So now all I have to do is put this one in front of a I hat and this one in front of a j hat, and I have the total vector f31. So f31 is 0.354 newtons I hat plus 0.354 newtons j hat. Now remember, our original fact was that f3 is equal to f31 plus f32. So now I have to add this vector and this vector. There's only a j component on this one, so this isn't affected at all. So I just write that down verbatim. But in this case, I do 0.354 minus 1, and I get negative 0.646 newtons in the j hat direction. Because obviously the negative 1 is bigger than the 0.354, so the negative sign wins. Now, that gave me the vector in component form, which is nice and succinct, but it's not necessarily that physically helpful. So I went ahead and showed you how to decompose it into, or excuse me, recompose it into a magnitude and direction. So you always want to take these and pay attention to their signs. This is a I hat, and the number in front of it's positive. That means it's going to point to the right on the x-axis. This one's a negative, and it's next to a j hat, so that means it's going to point down along the y-axis. So I drew it like that. That gets me the right quadrant and everything, so I don't have to use those stupid rules, you know, tangent is this in this quadrant and sine is this in this quadrant. I just look at it and I know immediately what it is. And I try to draw them somewhat to scale. They don't have to be perfect. So like this one, I knew for a fact, since this was almost twice as big as that, I knew this angle is going to be bigger than 45 degrees, because if they were equal, it'd be 45. And if it was smaller than 45, they wouldn't be equal. This one would be, in fact, a lot bigger. So I knew it was going to be bigger than 45. That gave me a sort of guess to keep myself honest. So I took the inverse tangent, and, you know, through our alley means tangent equals opposite over adjacent. So the tangent phi would have been opposite, which is the same thing as 0.646. Notice I dropped the sign. I don't deal with signs because it all fixes it by my drawing. Over adjacent, which is 0.354 newtons. That didn't have a sign, but I would have ignored that sign as well. So I do the inverse tangent of that number and got 61.3 degrees. And I just used Pythagoras to get this. So this squared plus this squared, take the square root, you got 0.737. So all of these have this extra digit right here that shouldn't be there by sig fig rules, according to the way I followed it. How does that work out? Does that make a little more sense now that you've recapped and seen how it was done?
Yes, thank you.
Yes.
No problem. All right, so that is a very classical, typical problem. You guys might want to try this, and actually your book probably has the example. Try putting that same charge instead of over top of the negative charge, put it dead center over the middle. You'll get a nice simplification that makes life a lot easier. This configuration here, we have two charges that are equal in magnitude but opposite in sign. That's called an electric dipole, D-I-P-O-L-E, and that comes up a lot. If you've ever heard of dipole antennas and stuff like that, that's really what this relates to. It's not really that much related to a dipole molecule, except a dipole molecule acts like this, okay? Meaning I can't I can't show you two charges separated, but that's exactly how a water molecule behaves. It behaves as if there's a negative charge on one end and a positive charge on the other end. So by knowing how this behaves, you know how a water molecule behaves. So it is fairly important. There's also a quadrupole and so on and so forth. It's basically any power of two poles. So a power of 2 to the 1 is a dipole, a power of 2 to the 2 is a quadrupole, a power of 2 to the 3 would be an octopole. And it turns out sometimes there's more helpful information from the dipole, quadrupole, octopole, and so on and so forth than you'd otherwise get. So for instance, one thing I've heard of is machinists have a really hard time machining a perfect sphere. That's not an easy thing for a machinist to do. So Oak Ridge was studying, I want to say it was gravity, but it might have been electric charge. It might have even been nuclear forces, but they needed a perfect sphere. Well, it turned out that if you break the equation for a sphere up into octopoles, dipoles, quadrupoles, 2 dipoles basically, so 2 to any power, the more poles you get, you add up, you get something that doesn't up close look anything like a circle, but in fact is more accurately a circle than an actual machinist can make. So the dipole stuff and stuff like that does become very important. If you become a double E, it'll be super, super important. So by all means, just remember that. That's why your textbook always goes through problems like that and so forth. So I've sort of tackled the two hardest type of problems, or the hardest type of problem you do, minus the calculus so far with Coulomb's law. And what I want to do is first off take and make Coulomb's law into a vector law in a sort of neat way, because I'm going to do the same thing with the electric field a little bit later. So let me show you what I mean by this. So let's imagine in three-dimensional space, I got an x-axis, I got a y-axis, and then I got a z-axis coming out of the page, which we represent as diagonally downward, okay? So let's imagine somewhere over here in space, I got a charge Q1, and over here in space, I have a charge Q2, okay? We know that the magnitude of the force, F, on 1 due to 2 is equal to K Q1 Q2 over R squared. So what I'd like to do is actually get this in terms of vectors so I could blindly, if I wanted to, blindly put in these vectors and automatically get a vector. So what we might think of is there is a vector that gives you the position of Q1, and that vector is R1. So it'd be like X1 I hat plus Y1 J hat plus Z1 K hat. And similarly, there's another vector, R2, that gives you the position of charge Q2. We know that the force has to act along the line connecting these two charges. Can anybody think of a mathematical operation you can do on R1 or R2 or both R1 and R2 to get a vector that is along this line right here in three-dimensional space?
Is that when you cross the vectors?
You could do that. That's a smart one. So if you actually took the cross product, you would get a vector that takes the plane of R1 and R2 and creates a parallelogram of it and calculates the magnitude of that parallelogram. But the problem with that one is when you cross it, it actually makes a vector that goes perpendicular to that plane. So it's the right idea, you're combining two vectors, but that's not the operation that would work because it gives one perpendicular to this plane, and we want it actually in that plane. Can you think of another vector that's in the plane with R1 and R2? I'm giving you a long pause because it's really a eureka thing if you can come up with it. what can you do with R1 and R2 to get another vector that's in the same plane as R1 and R2?
Is it the dot product?
Dot product is another nice operation, but that one gives you a scalar, so that we can't use that one. It's much simpler than you are thinking.
Can we just use the cosine law?
You could use the law of cosines, and that would give you the actual sum, for instance, of them. And the sum is pretty close, but remember the sum would point this way. Like you'd complete the parallelogram and it would go across that.
Yeah, you're right.
So we got one more. One more operation you haven't considered.
You can subtract them.
There you go, subtract them. So if these two charges were in fact both positive, which is what that, by putting it that way says, so if I end up putting it in negative, it's just going to flip the sign. And if I end up putting them both of them negative, it's going to flip them back. So everything's right, pretending these are positive. So if these are positive, then I want a vector that points from Q2 to Q1, and that will give me the actual vector that's important, the vector that's parallel to the force, right? So what I'm going to do is subtract them, but I want to get the arrowhead of the vector pointing here. So which subtraction do I do? R2 minus R1, or do I do R1 minus R2?
R2 minus R1.
R2 minus R1. So R2 minus R1 would be this. And then minus R1 would be basically this. And that means that vector would be this. You see that points the wrong direction?
Oh, yeah.
That's okay. That's good that you were trying. So now here's the deal. F12, we've now worked it out, is equal to K Q1 Q2 over, I'm going to leave it as R squared right now, but I'm going to change that in a second. And if I multiply this by R1 minus R2, which is what we just decided was correct, I'm changing the magnitude of that vector, aren't I?
Mm-hmm.
In other words, I'm taking the force and multiplying it by the magnitude of this difference of vectors. So really, if I'm going to do that, I need to divide it by that magnitude of that vector as well, which I'll call like that. Now I'm multiplying it by a unit vector. Does that make sense?
Does that say one R minus R2, or is that
R1 minus R2 over, and these are the absolute value bars that they use to indicate magnitude.
Oh, okay.
Does that make sense? Now, what is this vector? Can you give me that in terms of R1 or R2 or R1 and R2? Or what is this magnitude, not in a vector, sorry. How's the distance between them related to R1 and R2?
This?
I think you're right. Go for it.
Can you repeat that, please?
Okay. How is this magnitude R related to either R1 or R2 or R1 and R2 in any way?
Is that the magnitude of their sum?
Close. The magnitude of their difference.
Oh, okay.
So it's the same thing as that. So ultimately, here's our final expression. F12 is equal to K Q1 Q2 over R1 minus R2 cubed times R1 minus R2. Remember, there was already a power of 1 there, and now there's a power of 2 there, so it becomes R cubed law. But this is an actual formula. If you write out a vector that points from the origin to Q1, and if you write out a vector that points from the origin to Q2, and then you plug in Q1, Q2, and K, and work out the magnitude of R1 minus R2, this will not only spit out the magnitude, it will actually spit out the exact vector. So that's kind of neat, and it's a nice practice of seeing if you can do this on your own. So what I recommend is closing your book later and just, or your notes or whatever, and try to draw this diagram and come up with this on your own. We're going to use that a lot when we start to deal with vectors, when I'm dealing with the electric field. Now, we only got like 3 minutes left, so what I want to tell you is the problem with Coulomb's law is the same problem Newton and Einstein had with gravity. So Einstein and Newton both had problems with gravity. Newton knew it was a problem, but he's like, I don't care, I can solve problems, so I'm just going to use it. Maybe we'll figure something out later. So they solved this problem, which is called action at a distance. It's as if the sun reaches out and pulls on the earth, even though there's nothing touching them. So this similarly is if charge 1 reaches out over space and grabs charge 2 and pulls it, right? But there's nothing there. There's no strings or anything like that. So it's called action at a distance. They explain it, though, by conjuring up an idea that maybe the charge Q1 distorts space a little bit in some way, such that when Q2 gets in there, the space is touching Q2. And the space is treating Q2 and making Q2 move according to Q1's directions. So that's basically called a field. So that was ultimately how we solved it. And then the cool thing is it turned out we started making predictions about what this field would look like, how much energy it would carry, all sorts of cool stuff like that. And lo and behold, it turns out that thing we made up to make ourselves feel better about action at a distance turned out to be a real thing. So what we do is we take the electric field is what we're treating now, and we define that to be, you take the force from Coulomb's law and you divide it by the actual charge feeling the force. So in this case up here, it was the force on 1 due to 2, okay? So the force on 1 due to 2, the one feeling the force is 1, so we're going to take out Q1 in that case. But the problem is Q1 creates a field as well, and that could in some sense interact with the field E. So what we really want to do in the most extreme case is take the limit as Q1 approaches 0. It turns out there's really no practical problems with this. We just basically get that E2, which means the E field due to 2, is equal to K Q2 over R squared. And it has some R vector that I haven't worked out yet, so I just call it R hat, okay? It's still acting as if basically it's going to act along a line going through Q2 to the point in space that you're wondering what the electric field is. So in principle, we're going to drop all the 2's and just say an electric field E is created whenever we have a charge Q, and the magnitude of that electric charge, or excuse me, electric field, is KQ over R squared, and its direction points in the direction that a positive charge would move. That is ultimately Coulomb's law for an electric field. We can dice that up a little bit, make it a little fancier, and say that in fact the differential element of the electric field is equal to K dq R hat, oh that should have been a hat, sorry, R hat over R squared, only we're kind of sloppy when we're doing this as physicists. We can write the dq anywhere we want, and we have to understand that everything's being integrated even though this is after the dq and even though this is below the dq. So that's the rule. That's ultimately how we do integrals to treat electric fields of charge distributions. Like if I have a long string of charges and I want to calculate the electric field at some point, I'm going to use that formula. But I'm going to work it out just like I did here, finding R1 and R2 first. So I think that's good for today. We just barely crossed over the 12:15 mark. So we're done with this. We actually are in a good spot where you can do the vast majority of chapter 21. You can't quite do the integrals yet, but we're going to cover that on Tuesday. And actually, I'll even post a video of it before then if I don't have one already. I think there might be one already posted on Canvas as well as on my YouTube channel. So check that out. But do on your own, try to work out this. See if you can come up with this formula all by yourself. Okay, because if you can, it's going to be a breeze when I give you this one, because there's an equivalent formula for this one that's sort of like that one. Okay, so I did send out an email. Did you guys get my email, one about the YouTube channel and two about the lab?
Yes.
Yes. Okay, so I'm going to give you guys a break till 12:40. So if anybody wants to get something to eat real quick, now's the time. And then I'll call you, summons you back for the actual lab. Today's lab is actually pretty short too, but as long as we can keep this, I haven't received any emails saying someone has a conflict with this. So as long as we can keep this where we started shortly after, we're going to consistently finish almost a whole hour earlier every day. And some of the labs are kind of short, but some of them are kind of long. So this today one will be a pretty short one. So anybody have any questions?
What time's the lab starting?
12:40.
12:40. Okay.
So everyone, send me a chat so I'll have you on the roll, and then you're free to go. I'm going to wait for the last person to leave in case anybody has any questions. Y'all have a good day, and I will see you at 12:40 unless you're not in my lab.
I have a question.
Yes, sir.
Should we go, so like I've been connecting to the Zoom meetings by going to the calendar and clicking the join link. I should go to the physics 2 lab like module
Yeah.
on Canvas.
Yeah, L02, that's correct.
Got you. And then go to it that way.
Yeah, or you can pull up in your email, there's a link in it to the meeting.
Okay, awesome. Thank you.
No problem. No problem, Corey. If you haven't left yet, I saw that you came in late. I wondered what had happened, but that makes it feel better that you had just gotten disconnected earlier.
Hello, sir.
Yes, sir.
My name is Kadeem Henry. I'm new to your class. I just want to know, I know probably just came in. Are you going to be using master engineering for like homework and teaching, or I don't know?
Yeah, my lab and mastering is used basically for all the homework system. So basically that does all my homeworks for me. So I create homework assignments in there, and then you do them in there and it grades them for you, or for me.
All right. So is there any way for me to sign up for that, or?
Yeah, you finished 241 just recently, right? Like last semester?
Spring semester.
In the spring semester? Unless you bought one of those special deals, there are some special deals that save you money where you get only for 18 weeks or something. Unless you bought something like that, then your one from spring should still be good.
We never used mastering engineer. I had Dale Horton as my professor.
Oh, he didn't use that at all. Yeah, you're gonna have to use that here. That's a bummer. I forgot they all the campuses are supposed to be using the same book, and I know he went off on an experiment to try something. So that's probably what happened. Yeah, you'll have to get that, but the cheapest way you can do it is just click on that thing and buy it straight from there. That's gonna save you probably $40, but it's still gonna cost like $70. I apologize for that, but that's if I had an extra account, I'd be glad to give you one, but I don't, bud.
So just look it through your course and then do the registration through master engineer.
Yeah, go into the Canvas course for this course. You'll see a link up at the top left. It says My Lab and Mastering. Click on that, and it'll say like Get Started, and you click on that Get Started button, and it'll ask you to create an account at that point. They'll give you, I think they give you like a week or two free. So if you don't have the money right now, it shouldn't be a problem. But yeah, that's that. And if you have any kind of assistance, it qualifies so they can pay for it, but you might have to go to the bookstore to get that process. So if you have financial aid or GI Bill or something like that, I don't think they'll let you just pay and then get reimbursed. So you might not be able to buy it through them, but it's going to cost more if you go through the bookstore.
All right.
Anything else?
Trying to make sure I get all the questions. You have your syllabus.
Yeah, did you find my syllabus on the page?
Yes.
Okay. And yeah, I'm pretty good at my emails. I'm actually doing really good this semester. So also, if you think of something later, you can always email me. I pretty much am in email contact all during the week, and I'm usually actually more in contact than you'd expect on the weekends. But if it's a quick question, I usually answer that immediately. But I guarantee you to answer within 48 hours.
What book are you using? Are you using OpenStack or?
God no. But the good news is it comes with the ebook. So we are using, I forgot you use OpenStack. We are using the Giancoli textbook. It's Physics for Scientists and Engineers. But for that $70 price, you get the ebook and that. It's like, I think it's $69.99 or something.
Can I order through Barnes & Noble?
You can, but they mark it up. They call it a 30% markup, but it's actually more like a 42% markup. So it's going to be a lot more expensive that way.
No, I have the military covers me through that stuff. So
Gotcha. Yeah, then you can order it from them. You can even go through book brokers, all sorts of stuff.
Gotcha.
I'm sorry about the problem of you having the other semester with a different textbook. That's a bummer.
Yeah.
Is it still clearing out?
Did somebody ask something about lab?
Excuse me?
I heard somebody say something that sounded like lab, but I couldn't really make it out. Might have just been background noise. All right, well, y'all are free to go as long as you emailed me, or excuse me, you chatted your name to me, so I'll have you on the roll. As long as you do that, you're free to go. I'm waiting for the last person to leave, and then I'll sign off.
I do have, sorry,
no problem.
Because I'm trying to get used to your teaching methods. How do you teach and do things?
Gotcha. Yeah, I'm all about trying to just show you a bunch of examples of how to solve the problems, because in the calculus-based physics, that's pretty much the main thing. I try to get you to learn concepts, but through your reading of the textbook. So there's a concept set of questions for every chapter. And those questions count, I think, 5% of the course grade. And when you have a test, I usually have about 3 concept questions on each test.
All right. So how are you? Yes, for testing. Are you doing like how the way other professors are doing, midterm, final exam, or?
Yeah, so I'm doing, I do a test roughly every 2 weeks, something like that. And those are all online, but I do have a midterm and a final, and those are using Respondus Lockdown Browser. So you'll need a webcam and you need Respondus Lockdown Browser. I'm looking for cheap places for people to buy webcams in case you don't have one. Do you have one already?
Yes, I have a webcam.
What's that?
I have a webcam, sir.
Oh, good. Then you got no problem with that. But I am looking for, because some students don't have them, I'm looking for a cheap version of a webcam. But you'll need that because we use Respondus Lockdown and Respondus Monitor for the midterm and the final. And the midterm and final combined make up 30% of your course grade.
All right, sir.
All right.
That's all.
I do usually give you an equation sheet too, by the way.
All right, sir. Thank you.
Oh, by the way, on the other tests, the ones that aren't Respondus, it's open book, open notes, open Google. You can Google stuff. The only thing you can't do is communicate with another person about the test during the test or anything like that, nor can you go to a website that's been created since the test was opened. So other than that, it's fair game. But you're limited in time. That's the downside. And if you go over, it costs you a buttload of points.
Gotcha.
Okay.
Thank you.
You're welcome. Enjoy having you, Kadeem. Anybody else?
Yeah, I had a question when it came to the homework.
Yes, sir.
I'm just trying to go through and looking what's coming due and everything. Like I'm getting comfortable with, the chapter 21 stuff, but I'm looking here at the stuff that's going to be due, what is it, on Monday night, chapter 17, 18, and the physics primer. I'm looking through those, and looks like I'm gonna need the book to get through them. But I've been having trouble. I sent you an email about this, but I wanted to go over it again with you.
Okay.
I've been having trouble getting my book. I just called the bookstore today. They say it's not even going to be. It's probably going to be ready for me to pick up Tuesday.
Okay. So you know you have access to it just through since you're on My Lab and Mastering, you can go to the textbook from there.
I tried that and it said I needed to have a subscription, which I've registered and everything, and I'm just doing the 14-day
Gotcha.
14-day trial, and it's not letting me get the book. It's letting me.
Stinks.
Yeah. So I asked for if an extension is possible or not, but I'm not gonna have anything until Tuesday.
No problem. Just let me know when you do get that. I can give you an extension on those grades. So when you get your textbook, let me know and I'll give you an extension on all the assignments. And anybody else that has that same problem, of course, I'll do the same thing for.
Okay, awesome. I appreciate it.
No problem. Sorry for your problems, buddy.
It's GI. Well, it's not even a GI Bill. It's worse. So when it comes
If
to
it helps you, if you find anybody that has a calculus-based physics book, any book will help you with these first 2 chapters.
I mean,
So
I
borrow
got
someone's
the
book, you'll be fine.
OpenStax one
Uh-huh.
from my last semester, and I know that'll get me kind of going, but
Right. It feels a little better having the same book, even though I'm trying not to use examples from the textbook at all.
right.
My examples are my examples, and then you have the extra examples that the textbook gives, and then you also have the examples that I put on YouTube and on Canvas.
Right. I'll go through all of them too. So
I apologize. They're not polished, the YouTube videos and stuff. So sometimes there's like one of them that has a 9.5-minute thing where I'm just talking without the friggin' mic on like an idiot.
that's nice. Okay, no problem.
I usually warn you in the comments below, so check that before you start one.
Absolutely.
All right. Have a good one, Marcus.
All right. Thanks. See you in a little bit.
Michael, you have anything? All right. Well, I'm signing out, folks. I'll see you in about 10 minutes.